Okay, so we've been doing all this stuff with power series, and I know it's the end of the semester. I think I'm starting to feel like everyone's kind of losing the motivation. So I thought I'd start class today with two separate problems that will maybe help you believe that what we're doing is important. So I asked, if I asked you what sine of 1 was, what you would do to get that is you go to your calculator, right? So someone break out their calculator and type in sine of 1 and tell me what you get. 0.84. So are you in radian mode or degree mode? So why are you in radian mode, not degree? Because there's not a degree symbol, right? So if there's not a degree symbol up there, then that means 1 radian. So what did you get? 0.84. That's it? Just 0.84? There's more. Here. So you got approximately equal, because your calculator is going to stop at some point. So what does it say? 0.84. 984. Okay. Wow. All right. Now that is an approximate answer. Just like if I ask you what pi is, you type pi in, because some calculators have pi on it, you type in pi, it'll say 3.1415, right? And then it's going to stop at some point. So what did your calculator just do to figure out what sine of 1 was? Yeah, I mean, it's going to be a power series, but why is it a power series? Why is it that it can't do, like if we were asked something like this, sine of 30 degrees, how do we figure out what sine of 30 degrees is? How do we figure that out? Well, that's one of the common angles, right? So we had to memorize it, didn't we? We had to say, okay, you're 30 degrees on your unit circle, what's the y coordinate, right? Something like that. But otherwise, if we change it to 27 degrees, well then we learned in pre-cal that, well, you just have to use your calculator for that, right? But what's actually happening in the calculator? The calculator only any computer out there can only do 4 arithmetic operations: addition, subtraction, multiplication, division. That's all it can ever do, right? You all are aware of that, yes? Okay, so that's all a computer can do. Well, we're going to look at this again, but the question is, where does this number come from, right? Where does it come from? All right, now, the next thing is, if I asked you to find the antiderivative of this, let's say I wanted to integrate this function from 0 to, let's say, 2, all right? And I'm like trying to find the area underneath this curve. If you try and find the antiderivative of this function right now, you won't be able to do it, all right? There's no technique that we have. There's no technique out there that will allow you to integrate this function. Some functions are not integrable in the sense using the techniques that we have. So there has to be some way, hopefully, that we could do that, right? So with those two ideas on board, let's tackle them one at a time. Then we'll get back to the lecture, right? But I just want to, again, try and motivate what we're doing here. So I have a special power series I'd like for you to look at. And right now, don't ask me where it comes from. We will actually generate this power series later, okay? But this is the power series, sum n equals 0 to infinity, -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. So if I plug in 0, I get something, plug in 1, plug in 2, plug in 3. If you do that, here's what you get. All right, there's the series. You see it? X minus x cubed over 6 plus x to the 5th over 120 minus x to the 7th over blah, 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 blah. And I'm showing you the first, 7 pieces or 8 pieces of it. But, I mean, I could just keep going all day with this power series if I wanted to. I could show you the first 28 terms of it, okay? But I'm just showing you the first 7. Is that okay? Now, what would happen if I plug the number 1 into this? See, because this expression right here, this is a power series, right? So if I look at it as a function of x, and I ask you to plug 1 into it, then you'd plug 1 in here, 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 right, for x? Yeah? And then it would spit out some number. Like if you stop somewhere, it would spit out a number. So I'm going to actually have the computer do that for me. I'm going to take it all the way back to the beginning. Remember, my power series is right here, okay? So right now, if I start with the very first piece, and just look at the first, if I just cut it off after the first term, and then replace that with 1, I'd get 1, wouldn't I? So if I plug in 1 into that series, my partial sum is 1. And look, I've got this going out 40 decimal places, okay? Because I want you to see what happens. Now, what if I do, instead of the first term, the first 2 terms of that power series, and replace this with 1 and this with 1? Look at the value. This is the value. Got it? 0.833, right? Okay, now let me go out another one. Now I've got the first 3 terms of it, right? And check that out, 0.8416, okay? Keep going, keep going, keep going, keep going. Let's go to there. Look at this number right here. Now what did your calculator say a second ago?
0.84147.
7? 0? 984. Okay, good. So it looks like I've got that answer right there, don't I? But I've actually got more than that. So let's see. This is going to be kind of tough to do, but I'm going to have to make this smaller so we can see it. Let's make this big. Okay, so now what I'd like for you to do is let's see if I go out another unit or another step on this, what changes in this. Okay, so it looks like, let's see, we went out this far. Did that change? I'll go back. That 7, that 8 doesn't change, right? That 9 doesn't change. Looks like right there. Do y'all see that? It's changing right here? Yes? Okay. So that means that if we just do the first 1, 2, 3, 4, 5, 6, 7, 8, if we just look at the first 8 terms of that power series, we actually have the sine function, sine of 1, accurate out to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 decimal places. That's how precise this sum is. That's how close it is to the true value of sine. Does that make sense? And if I go further, let's see what happens. So that one's changing. Oh, that one stopped changing. Let's see. What's changing? Oh, shit. I'm not clicking it. Got to click it. So wait, it's still changing? No? Where is it changing? I'm too close to the board. Oh, there. No, it changed there. Something. It's still looks like, okay. Well, do you kind of trust me on this? That it's what's happening is as we march out further, this gets more accurate. I'm going to take it out as far as I can go. I'm going to go out 50 terms. All right? And now let's take a look at that number down here. Well, that's still all the terms. Hold on, I've got to get down to the number. There we go. You see the last 2 numbers? 5821? Yes? I'm going to back it up. I'm going to back up 1 to the 49th, and let's see if it's still 521. Or 5821. It's the same thing, isn't it? So if I go out 50 terms on that power series, I've got the value, sine of 1, accurate to 40 decimal places. Now, you may argue, well, that's not really what sine of 1 is, right? Right? You may say, well, that's not really sine of 1. Just like pi would keep going forever, right? This may keep going forever too. But if I'm building an aircraft and I need to make a ball bearing that has to be, milled out of a machine that has to be very precise, you work with metal. I mean, you think 40 decimal places, you can't even, there's no machine out there that could be that precise, So a lot of times in the real world, we don't need to go this far. So if you have that number within maybe 6 decimal places, you're good to go, right? So in the real world, the power series can take place of functions that we deal with. And the great thing about the power series is that, what do you need to compute a power series? Let me go back here. To compute a power series, you need to just be able to do a bunch of addition and subtraction, right? And you need to do, x to a power. That's okay, because if I plug a number in here and raise it to a power, you may not want to do it, right? But a computer sure as hell doesn't mind doing it, right? If I say, hey, take 1.25 and raise it to the 13th power, you don't want to do that. But your computer has no problem doing 1.25 times itself 13 times. It's going to do it in an instant, isn't it? So a computer is calculating this. I mean, obviously it's doing it, right? I'm not slowing my computer down here, right? So this is basic arithmetic done by a machine that is basically evaluating a function for us. Does that make sense? So the question becomes, what functions out there can be converted to a power series, right? What functions can, what functions can't? And it turns out that basically almost any function out there can be converted to a power series, all right? That means everything that you've already seen in your life, everything we've ever studied, can be converted to a power series. And so our goal here is to first understand power series, this whole idea of convergence, and then the main goal is to take functions and turn them into their power series, all right? So now the second problem that I put up there was that integral we couldn't solve, right? So to get to that, I want to show you, oh, it's still here. I was doing a lot of coding up today here. Okay. I thought I would motivate this with another example, or with a visual here. Get over here. Where are you? There it is. Okay, so I was just looking at sine, wasn't I? And we did sine of 1. And I said what we do is we take that power series and we just plug 1 into it. But if I leave it as a power series and graph it, what does it look like? So you know how we had all those little x to powers? What if I just graph that as a function? So I'm about to do that for you. So here, the red function here is the true sine function you learn in pre-cal. What you're going to see up right here is I'm going to start introducing the power series. So the first term was x, right? So this is me graphing x. X is a line, right? Y equals x. Now let me get the next term of the power series, which was that x minus x cubed over 6. So now I have a cubic, don't I? And doesn't that black cubic function look like it lands pretty close to that sine function? Except for the fact that this end, it's like, it's pretty good, and then it's like, no, that sucks, right? Well, I'm only 2 terms out. Let me go further. Now I'm 3 terms out. Look at this. Check this function out. See, it's now starting to pick up this curve. And now I keep going, and just watch the black function as it marches its way out and starts to cover up the red function. Isn't that freaking amazing? I think that's amazing. You're basically taking a sine curve and you are fitting an infinite polynomial over it. And basically, if this goes out to infinity, they're the same function. That's pretty cool. And you can do that with any function. So back this back out. How about cosine? Yeah, sure, we can do cosine. There's the power series for cosine. Okay, so did you see me kind of map it right on top of the cosine? Has anyone noticed anything about the cosine, the difference between the cosine and the sine in the power series? There's something very, very fundamentally different. The powers of this are what? Even, and the powers on the sine were odd. I wonder if that's where they get their name, even and odd functions. It is exactly where they get the name. Okay? So like we always learn even and odd as being like symmetry, certain types of symmetry, but in reality, it comes down to its power series. If the power series turns out to be a bunch of odd powers of x, then it's an odd function. If the power series turns out to have a bunch of even powers of x, then it's an even function. And what if it has both, odd and even? Then it's not odd, it's not an odd function, it's not an even function, it's just, it's just a function, right? So what's an example of that? How about the tangent function? So look at this, something different is about to happen here, tangent. I'm going to try and, right now I'm approximating it with 0. Here comes my first piece, boom, x, not very good, right? I'm trying to be red, and the black one's trying to be the red one's not doing a good job, is it? Okay, so I go again, okay. Oops, hit the wrong button. Go again, look at this. Awesome. What happened? Oh, I'm slowing my computer down. I'm slowing it down. It's thinking. I think it's done thinking. I think I went too far. I got pushed the limit of what bring it back in here. There it is. Okay. There. Okay. Now, is tangent an odd function? I think I said it wasn't just a second ago, but it's an odd function. Tangent is odd. And you can tell just by looking at its power series, right? Now, do you see something that's different here than with the sine and the cosine? What's that? Okay, so there's no subtractions. But in terms of the picture, I'm trying to fit this black curve on the red curve, but notice that it's only doing a good job right here, right? It's only doing a good job right here. Like, what if I wanted to fit it over here? This power series is no good, right? So do you remember last class that we learned that all power series can be written sum n equals 0 to infinity c sub n, then x minus a to the n? And we talked about what this a is, right? Were you the one who talked about the shift, right? Okay, so we were saying we want to shift it over. Well, that's because if this black one is doing a good job right here, but not over there, then I can just change my a and that'll move it over here, and then it'll map good. Does that make sense? Now with sine and cosine, it didn't matter because it fit right away, didn't it? This right here, the range at which, or the x values, the domain at which this black function works is actually going to be defined here today. I'm going to actually call that the interval of convergence, but I'm just trying to visually get you to see it right now. Okay, let's do another function. What else do I have in store for you? Let me go back up. Let's go back up. Here's an interesting one. See this weird? This is a rational function. So there it is. Now here I come. You see it just marching its way out? I'm slowing my computer down. I'll let it catch up. All right, there we go. So do you see over here, it's really good, right? It's really good, and then right in here, it starts to do this, right? Well, I just have to go out further, and what's going to happen is it's just going to keep doing this, and it's going to just keep going, and it's going to work its way out there. It's an infinite series, okay? So I'm not worried about it ever stopping. Now, I could also do a shift, and if I move it over here, it's not going to do a good job at this, but it's going to do a real good job in here. I hope this makes sense. Okay, one last one then. I need to change this because I didn't put negative in the code. E to the negative x squared. There's the graph of it. There's the graph of e to the negative x squared. And I'd like to fit that black curve on there. Ready? Here it comes. It's doing a fabulous job, isn't it? Isn't that doing a great job of doing that? So, if I was going to try, if I wanted to integrate this function from 0 to 2, which is what I said before, instead of integrating that, I can integrate this. And so I could do the integral from 0 to 2 of this. Now, how far would you go out? Well, I don't know. I mean, again, depends on how precise you want to be. But I could stop it here and say dx. And then each of these would be easy to integrate, wouldn't they? You do them term by term. These are all just powers. So you could just do power rule on each one of these. So the antiderivative of this would be, let's just get it started. It would be what? X minus 1/3 x cubed, and then plus, let's see, something like 1/10 x to the 5th plus dot, 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 right? I would have more of these. And then I would just evaluate 0 and 2. So I plug 2 in here, get a number, plug in 0, get a number, subtract. That's the area under the curve. Make sense? You don't need to, we don't have to worry anymore about the fact that that function cannot be integrated with any technique of integration. We still have a way of doing it. Here's what the antiderivative looks like. Okay? So I hope that that gives you a better framework of what we're trying to achieve. Now let's get back to the notes. All right, so we ended the class last time. We were talking about power series, what a general power series looks like. Here's what it is. This is called a power series about A, or sometimes you'll hear this is a power series centered at A. Right? There we go. Now, we want to know that if we define this power series as a function, we want to know for which values of x the series will converge. To do that, to figure out where a power series converges, we will use the ratio test. And the ratio test, what we want is for the ratio test to give us something less than 1, because that will give us convergence, right? But the ratio test fails when it's equal to 1, so that will force us to test the endpoints. So I'm going to start with an example, and hopefully you'll kind of pick up. I can't do anything about the temperature in here, sorry. I guess I could cancel class, right? We could do that. And what better way to start than with a famous power series? A famous power series that is used in problems that involve heat transfer, how heat dissipates through a membrane, like a thin piece of metal or something. Or this is also used to model vibrations on a drum. So this is called an order 0 Bessel function. And don't get yourself too concerned about the fact that, oh, this is a Bessel function. What does that mean? I'm confused already. Just understand that it is a function, f of x, okay? It's order 0, which means there's a 0 here. And here's the definition of this function. Sum n equals 0 to infinity of -1 to the n, x to the 2n over 2 to the 2n times n factorial squared. That's an order 0 Bessel function. And this function was also used to help model planetary orbits. But this is all, you can look up history of this if you want. But this is a function, okay? Just like the function square root of x is a function. This is a function, all right? We want to know what the domain of it is. That's asking you for what values of x, will this sum converge to a number, right? So for what value of x will I have an output for the function? Well, how do we do that? How do we determine whether the domain of a power series? Ratio test, right? So I've got to set up a ratio test. So here I come with the ratio test. And remember, the ratio test is I'm going to take the limit as n goes to infinity, the absolute value of a sub n plus 1 over a sub n, right? And what we want is that to be less than 1. So a sub n for us is this big, nasty, ugly looking thing, right? A sub n. That's a sub n. So a sub n plus 1 is that expression with all your n's replaced with n plus 1s, right? Okay, so let's do it. So this is equal to the limit as n goes to infinity, absolute value. All right. First piece here, this becomes -1 to the n plus 1 times x to the what? 2n plus 2, right? So you're really doing 2 times n plus 1 right there. That's what you're doing right here. And you're distributing the 2 through. So it really becomes 2n plus 2, right? Over this with n replaced with n plus 1. So 2 to the 2n plus 2 again. And then this one's a little tricky, so be careful how you write this. We're squaring something, right? But what are we squaring? N plus 1 factorial, right? So I need to write that n plus 1 in parentheses factorial. So this is just a sub n plus 1, right? Then I have to divide it by this. But dividing by this is the same as multiplying by the reciprocal. So I'm going to just multiply by the reciprocal here, 2 to the 2n, n factorial squared over negative 1 to the n, x to the 2n. There we go. And that looks pretty horrible, but a lot of things are about to get real nice with this, all right? Yeah, I'm going to split those powers up. Now, let's eliminate these negative ones. These don't even matter, right? Because negative 1 to any power, when you take the absolute value, it's going to go away. It's just going to become a 1. So those are not relevant to us. So we can just eliminate them. Miller time. I don't know why. What? See, I'm distracted. Who did that? Cold beer? All right. Limit n goes to infinity, right? I'm going to rewrite this as what? X to the 2n times x squared. And on the bottom, this is going to become 2 to the 2n times 2 squared, which is 4, right? But I'm just going to put it there so you see what happened. This one, a little tricky. Because up here I have an n factorial squared, right? I would really like it if I could somehow cancel these. So could we rewrite this? First, like what's in here? Isn't that n plus 1 times n factorial? Right, that's that peeling off of one of the factors. So I'm going to rewrite this as n plus 1 squared times n factorial squared. So what happens is, since there's multiplication between these, and these are being squared, I can square each one of these factors. And when I square the n plus 1, I get n plus 1 squared. When I square the n factorial, I get n factorial in parentheses squared. See how nice that's going to be? It's going to cancel out. Over here, I'm not going to do anything. 2 to the 2n, n factorial squared over x to the 2n. There we go. Now, a bunch of stuff cancels, right? X to the 2n's gone. 2 to the 2n's gone. N factorial squared's gone. And that's it, right? That's all that goes away. So here's what I'm left with. And watch how I write this. Because my limit is having n go to infinity, x has nothing to do with the limit, right? So what I'm going to do is I'm going to write things, the only thing that has x in it, right, is the x squared. I'm going to put that over here, still in the absolute value, but then next to it times I'm going to put everything else. So I'm kind of like isolating the x part from the rest of the expression. And the only thing left on the is what? 1 over 4 times n plus 1 squared. That's it. That's all that's left. So what happens as n goes to infinity? This goes to 0, right? And so our question was, can we let this, is this thing going to be less than 1? Like we said, for what values of x will this stay smaller than 1? And it turns out any value of x will work because this is going to go to 0, right? So this is headed to 0, and 0 times x squared, well, that's going to be less than 1, right? Now, I had a student in my other class say, well, what if x is infinite, right? What if x is infinity? Then you have an indeterminate form. You have something going to 0 and something going to infinity, right? Well, the idea is this. Infinity is not a number that you can plug into a function. You cannot say, hey, plug in infinity into this, right? We can do a limit and ask ourselves what happens as x goes to infinity. But if I plug a fixed number in, this could be a huge number, you know, a billion raised to the billion raised to the billion squared, right? Doesn't matter. This is going to 0, so that will eventually kill this thing off, all right? So this holds for all x, right? This means this ratio test checks off as being good and tells us that the original series converges, right? So we're saying that this right here, that Bessel function, has a domain of what? All real numbers. Everything. So you know how a second ago I was I graphed the red sine and then I came in with that power series and it kind of laid itself out over the sine function? And it would have kept on doing that in both directions forever. This Bessel function, if we were to graph it, would exist, the whole picture, I mean the picture would go in both directions forever. Does that make sense? Because we can plug any number we want into it. All right. This brings us to our next kind of note for today. Make sure there's not another example. Yeah, I don't want to do another example. This is a very important theorem. And here's what it says. I'll do this, go slow here. This is all in the book too, so you don't need to necessarily copy this all down. The theorem says that if you're given a power series, that there are only three possibilities when it comes to where it converges. So when we say where it converges, we're talking about the x values, right? Like what x values make it converge. We just saw in the Bessel function all x's worked, right? So that means the entire number line, everything. But there's only three possibilities when it comes to that. First of all, it could converge at a single point only, which would be if you let x be a. If x is a here, right? If that's a, that's 0, and you're adding up a bunch of zeros, and that's nothing, right? I mean, that's going to converge, yes? Okay. So you could have that your function is only valid at one point, which would be a pretty boring function, wouldn't it? It's like a function that you can only plug one value into it, and you can't plug anything else into it, right? That's one possibility. The other possibility is that it converges for all x. That's the Bessel function we just saw, right? And then the last possibility is that our function converges, or our power series converges on an interval, on a single interval. And that interval, the way we say it is that there's some capital R, which is a number, where the absolute value of x minus a has to be less than that R. Now I'm going to go through an example so you'll understand this better once I work through an example. But what we're saying is that on a number line, there's like where is it down there? So your x value can come anywhere out. Your x's that are valid can come from anywhere in this interval. So it's going to be a, I forgot to put a in the middle. So there's some number a. Okay. So remember, didn't we say that when x was a, it converged? Right? We said it in the very beginning, right? Okay, so automatically we know 1 point for sure. So at x equals a, it converges. But if it converges somewhere else, it either converges everywhere, like both directions forever, or it's some distance to the left and to the right of a, same distance both ways. So do y'all see, we call that distance r the radius of convergence. So it's like from a, if a is like the center, then to the left by r and to the right by r gives you kind of like a radius like on a circle, even though it's a straight line. Okay, so that capital R, called the radius of convergence, is something we're going to have to find. Right? And then the interval that we get, the interval where x is between two numbers, is called the interval of convergence. We're going to have to find that also. And we have to keep in mind that when we talk about an interval, you can have 4 types of intervals. You can have a closed interval, where you're including both endpoints. You can have, this is called a half open or half closed, however you want to look at it, where you don't include left endpoint, you do include the right, or the other way around, or you don't include both endpoints. All right? So we're going to do a problem now. And we did something similar to this, I believe, at the end of class last time, where we had to check the endpoints. But now, I guess the big thing is we have two new definitions here, radius of convergence and interval of convergence. We've defined something new. So we're going to go ahead and work through an example. So you know how I was showing you that picture of the sine one, and it went both ways forever? But on some of the ones I showed you, like the tangent, it only looked good for a little section. Well, that little section is the interval of convergence. That's what we're finding here. All right? So we're trying to figure out if somebody gives us a power series, like this one, where is this thing good? Right? Where is it valid? Here we go. Go ahead.
Are we going to use the ratio test again?
Absolutely.
This is just a question. Could we use another test?
Could you use what?
Could we use another test?
Yeah, but you're limited because it alternates signs. You see how we have a negative 5 to the n? You could look at that as a negative 1 to the n times 5 to the n, right? That's the same as negative 5 to the n. And so that's an alternating series. So that does restrict what you're allowed to use. Could you? Yes, but that's why I said the ratio test is the big daddy, okay? Because it's very useful when it comes to this. All those power, yeah, kills the alternating off, and all those powers become like n plus 1s and stuff. They all start to cancel. And that's good, right? Okay. All right, so here are the questions. There's two parts to this question I'm about to ask. First of all, find the radius of convergence. Radius of convergence. My 8-year-old daughter, my 9-year-old daughter is you'll understand when you have kids. Find interval of convergence. Is a way better speller than I am. Actually, he's a better speller than both myself and my wife. My wife asked me last night how to spell scarred. I was like, scarred? I was like, S-C-A-R-D. S-C-A-R-D. R-E-D. That scared my daughter. Was like, no, that's wrong. What's that? I won't let that happen. I'm not going to tell her what to do, but I won't pay for her to go to college for that. Okay. I hope that didn't come out on camera too loud. All right, so we need to find two things, right? Radius of convergence. So when it comes to the radius of convergence, here's what we're looking for. We're trying to figure out this capital R here, all right? We need to somehow figure out what the restriction is on x that's going to make this thing converge. So we start with the ratio test, all right? Just like we have before. So let's set up our ratio test. Limit n goes to infinity. Okay, negative 5 to the n times negative 5 times x to the n times x over square root n plus 2 times square root of n plus 1 over negative 5 to the n x to the n. All right, take a moment to look at that and make sure you understand where all those pieces came from. And now would be your opportunity to ask me if there's anything in there that you don't get. This is a sub n plus 1, right? But I've already done the splitting of everything. And then also, when I put n plus 1 in here, it's n plus 1 plus 1. So that just became n plus 2. Then that's just a sub n flipped over. So we're good? Okay, let's cancel stuff. Bye-bye, 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 bye-bye. And what about that negative 5 there that's still there? It's going to become a 5, right? I mean, the negative is not relevant. So this is going to become the limit as n goes to infinity. All right. Now, just like I did before, I'm going to split the things off that have x in them, right? The only thing that has x is that x that's sitting there, right? X by itself, right here. So I'm going to put that over here. And then in front of it, I'm going to put whatever else I have, which I had a 5 right on top, right? This 5. And then I have that root and that root. So can I write this? Is too much stretching too much, or is that acceptable to you? I put those two roots into one root, and the reason I did that is because I'm about to take a limit as n goes to infinity. I'm going to pass the limit through into here, and then once I'm inside, I've got infinity over infinity, and I can do L'Hopital, right? So that's this right here. When I do L'Hopital, is going to go to what? 1. Root 1 is 1. 1 times 5 is 5. So when I take my limit here, I get absolute value of 5x, right? Now, we need this to be less than 1 for it to work, right? That's what the ratio test tells us. We need the absolute value of 5x to be less than 1. Now, remember, this is what we're shooting for here. We need to get an expression that looks like this. Okay? We are trying to make this look like this. So the problem that we have with this is that we have a 5 in front. See here? This is a 1 in front of our x. So all we have to do is get rid of that 5. So first, this is the same as 5 times the absolute value of x, less than 1. I can do that because 5 is a positive number. So absolute value of 5 is still 5. And then you do absolute value of x separately. And now divide both sides by 5. And you get x must be between, or sorry, the absolute value of x must be less than 1/5. Now, does that look like this? It does. This actually does look like absolute value of x minus something less than 1/5. Minus what? 0, right? That's what that is. And so this power series right here that we're looking at, where is it centered? At 0, right? Because remember the definition. If you have a series that looks like this, I told you that this is a power series that we say it is centered at A or about A. A is this number, okay? So if it turns out to be 0, then this is a power series centered at 0. Now, what is the radius of convergence of this power series? The number 1/5, okay? So it's like, if we look at a number line, here's 0, right? 1/5 means we go to the right 1/5, we go to the left 1/5, and we know that in here, any value of x between here and here is going to make this series converge, all right? So if I graph this, if I were to graph this, the picture would exist between negative 1/5 and 1/5. Outside of that, it's not going to work, okay? You all right with that? Okay, now, we've answered the first part. Radius of convergence, capital R equals 1/5. That's our answer. The interval of convergence is just asking us for a little bit more information, but it requires a lot more work. Because to find the interval of convergence, I'm not asking how far out each way I go. I'm really asking, do I include those endpoints or not? Are we including 1/5? Are we including negative 1/5? Are they included? Right? That's what the question's asking. Because you have to go back to the ratio test here. If we look at this statement where we were, right here, if x is 1/5, then what is this number here? 1. And so that the ratio test would be giving us 1, and when that happens, it's inconclusive. If we put negative 1/5 in here, take the absolute value, we get 1 again. So those are the two, like, we don't know points, right? So let's go ahead and do that next part, which would be part B. So for part B, what I'm going to do is I'm going to start with where we were, which is right here. Right? I'm going to start with that. And now I'm going to convert that into an inequality without the absolute value. So I showed you this last class. You drop the absolute value, right? And then what do? You add another one over here, greater than, and then over here you change the sign. Okay, so I drew that picture for you a second ago, didn't I? X is, between those two. But now we have to check the endpoints. So which one would you like to check first? Negative 1/5. So we come in here and we say let x be negative 1/5. And do what? Plug it into the original series. We have to go all the way back to here and replace that x right there with negative 1/5. And when we do that, we no longer have a power series. We just have a series like in the previous sections, right? There's no more x expression. There's no more expression of x in here, right? X has now been fixed as a number. And we get something really nice here. Since these are both to the nth power, we can put them together, right? You can multiply negative 5 times negative 1/5, which would give you positive 1 to the nth power, right? But positive 1 to the nth power is just 1, right? Okay. Does that series converge and justify it? Yes? Why? You have to be able to defend that. Oh, almost like a p-series. Like if this was just square root of n, we'd be done right now because that would be a p-series, wouldn't it? Yes? But it's n plus 1. So you have to show it now. Right? So how are you going to show it? You want to do a comparison test? That's fine. We can do a comparison test. Would you like to do, what do you want to compare it to? Oh, by the way, you're on the right track. In my other class, one of my students said, yes, it converges because that goes to 0. The series converges because that went to 0. And what did I tell them? I told them, get out of here. So get out of the classroom right now. If that goes to 0, that tells you nothing, right? Okay, so that's the end term test failing, basically, right? So, yeah, I told them not to come back. All right, so we need to do this. We need to show that that converges right there, or diverges. And you want to do a comparison test for that. So compare, and what do you want to compare it to? So we're going to say a sub n is equal to this one. And you want to compare it to b sub n, which is what? 1 over root n. And that's a great candidate because Sophia already pointed out this is a p-series, right? We know what this one does. This is p-series. P is a half, right? And that's less than 1. And what happens when you're... diverges. The way that I remember it is this. If the power on this n is big, right? Like 2, 5, 10. So imagine like n to the 10th power. This thing is getting small really fast, isn't it? And that's going to converge. But if it's a root, then it's not, the bottom is not, it's getting, this is getting bigger, right? But this fraction is not getting small fast enough. I don't know if that helps, but if not, you have a sheet, right? Look at it, p greater than 1. Okay, diverge. So if I'm going to do this, what would you like for me to do now? I agree comparison looks fine, but what would the comparison, what would you actually do now? If A is, okay, so you're using the comparison test. If this series diverges, we have to show that this one is bigger than that one, right? So one option we have here is that we could say we want to show that 1 over root n plus 1 is bigger than 1 over root n, right? If this diverges, we want those to be bigger. That way, if this blows up, that blows up, right? That's one way. Or what would another option be? Limit comparison. That would be another. Or, so if you don't like that one, we could do limit n goes to infinity of this one over this one, right? So 1 over root n plus 1 over 1 over root n. And what would we be hoping to get here when we take this limit? It's on your sheets. You don't want to look? It's got to be a positive real number. We would be hoping that this limit comes out to be a positive real number. And if it does turn out to be a positive real number, what would it tell you? That they both go to the same thing. So if this diverges, that diverges. So, do you all have a preference on which one we do? This one's going to work. This one actually fails. Look, this inequality is not true, and you can see it right now. Numerators are the same. This denominator is bigger than that denominator, right? So this fraction would have to be smaller. Now you could cross multiply, and if you cross multiply, I think it's obvious there that the left side is not bigger than the right side because you're adding 1. So that's no good. So remember, this not working. Did we talk about the pregnancy test? Yeah, so this is the failed pregnancy test. Different test. This is the $6 HEB brand, and then this is the, I don't know. I've only bought the $6 HEB. Oh, I'm just kidding. Root n over root n plus 1, right? I'm flipping. Limit n goes to infinity. Root n over n plus 1. Put them into one root again. And luckily for us, that's 1, right? And that's positive. It's a fixed number. It's not. If this turns out to be infinity, the test fails. So this is a positive constant. Check. So that means whatever this one does in a series, that one does, so it diverges. Which means what? Don't lose sight of what we've just been doing. We do not want negative 1/5 in our answer, right? We do not want. So therefore, the series n equals 0 to infinity, negative 1 to the n, negative 1/5 to the n over root n plus 1 diverges. So don't include x equals negative 1/5. Okay, halfway there. We have to do the same for 1/5 now. Yeah, it was. Thank you. It was negative 5 to the n right there. Thank you. So now we test the other endpoint. Let x be 1/5 this time. Sum n equals 0 to infinity, negative 5 to the n, 1/5 to the n over root n plus 1, which turns out to be sum what? This time negative 1 to the n, okay? Not positive 1, so we can't just get rid of it. And then over root n plus 1. But actually, aren't you happier to see that than the previous one? Why? Because we have a test for this alternating series test which is pretty easy to employ. We just have to show two things. We have to identify the positive part. So we have to identify the part of it that's not alternating right here. And we call that B sub n. And then we show two things. What two things? Decreasing, we show it's a decreasing sequence, and then we also show that the limit of this sequence goes to 0. Right? Now, someone might come in here right now and be like, well, wait a minute, man. You said the ratio test was the best. So why don't we just do a ratio test on this? Seem reasonable? Well, where did we get 1/5 from? Didn't that come from a ratio test? And the ratio test turned out to be 1 when we plugged in 1/5? If you do a ratio test on this, you're going to get 1, which means it's inconclusive. So once you get past finding capital R, when you get to the two endpoints, you will never use ratio test for those two endpoints. You'll have to use something else. All right, but this one's okay. Alternating series test. First part, want to show that B sub n is greater than or equal to B sub n plus 1. So this would show that it's decreasing. So we take this, and we want to show that it's bigger than this with n plus 1 plugged in here, which would make that n plus 2, right? Is that true? Yes. You could cross multiply if you want. Root n plus 2 is bigger than or equal to root n plus 1. I think that's a point we could all agree. That side's bigger than that side. So first thing's verified. Second thing that we have to show is what? Limit n goes to infinity of the B sub n goes to what? 0. And it does, right? That's an obvious limit. Therefore, I'll just cheat and use this again. Therefore, this series with positive 1/5 in there converges. Doesn't it? Why does it converge? Because it satisfied the alternating series test. And if it satisfies both those conditions, it's a convergent alternating series. So it converges. Therefore, include positive 1/5. So our final answer. So this series converges on the interval we do not want negative 1/5. We do want positive 1/5. If you don't like that notation, you could put x greater than 1/5 less than or equal to negative 1/5, 1/5. That's it. It's a lot of work to get that, huh? So would you agree that if I give you a power series and I ask you for the radius of convergence, there's some work involved, but you're just going to run the ratio test, aren't you? But if I ask you for the interval of convergence, well, then you're going to expect to see at least two separate series problems that you have to do at the end, right? And I don't have my book, but I believe your homework assignment asks you for both the radius of convergence and interval of convergence for a bunch of problems. So that's pretty much it for this section. I'm not going to do any more examples. You need to go do your homework now for this and get your hands dirty. And they will get dirty. So in my, I've done the homework solutions for the whole